Imagine a sound so deep, so quiet that you don't hear it with your ears, but you might feel it in the silence between stars. A hum, not loud, not sharp, but constant, always there, filling the emptiness of space. Not a sound made by any instrument, not a vibration carried by air, but something more fundamental. A pulse in the fabric of reality itself. For decades, we looked up at the night sky, believing the universe was slowing down, that gravity, the force that pulls everything together, would eventually win. But in the late 1990s, something changed. Astronomers studying distant exploding stars made a discovery so shocking it turned our understanding of the cosmos upside down. The universe wasn't slowing down, it was speeding up. Something was pushing space apart, faster and faster, and whatever that is, we call it dark energy. But if we could hear the universe, we might say it's humming, a cosmic hum, silent, invisible, and yet shaping the fate of everything. Let's take a step back and understand what this means. For most of the 20th century, scientists knew the universe was expanding. Edwin Hubble proved that in the 1920s, galaxies are moving away from us, and the farther they are, the faster they go. It was like watching dots on a balloon stretch apart as it inflates. Everyone assumed that, over time, gravity would slow this expansion. After all, gravity pulls things together. Stars, galaxies, clusters, all held by gravity. So it made sense that the expansion would gradually ease, maybe even reverse one day in a big crunch. But in 1998, two teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were measuring distant supernovae, specifically Type 1a supernovae. These are special exploding stars that shine with a very consistent brightness, like cosmic light bulbs. By measuring how bright they appear from Earth, we can calculate how far away they are. And by studying their light, we can see how fast the universe was expanding when the explosion happened billions of years ago. What they found stunned them. The supernovae were fainter than expected. That meant they were farther away than they should be, which could only mean one thing. The expansion of the universe wasn't slowing down. It was accelerating. Something was pushing space apart, and it had been doing so for billions of years. This force, invisible, undetectable by normal means, became known as dark energy. Now, here's where it gets strange. Dark energy isn't a force like gravity or magnetism. It doesn't pull or push in the way we're used to. Instead, it seems to be a property of space itself. Think of it this way. As new space is created between galaxies, that new space also contains this energy. So the more space there is, the more dark energy there is. And the more dark energy there is, the faster the universe expands. It's a feedback loop, and one that has no end in sight. Right now, dark energy makes up about 68% of the total energy content of the universe. Dark matter, another invisible component, makes up about 27%. And everything we can see, stars, planets, galaxies, you, me, all of that is just 5%. That's right. Everything we've ever known, observed, touched, is just a tiny fraction of what's really out there. So when we talk about dark energy, we're not talking about something small or insignificant. We're talking about the dominant force in the universe, and we have no idea what it actually is. Let's clear up a common confusion. Dark energy is not the same as dark matter. They both have dark in the name, and both are invisible, but that's where the similarity ends. Dark matter pulls. It's a kind of unseen mass that holds galaxies together. Without dark matter, galaxies would spin apart. Stars would fly off into space. We know it's there because of the way galaxies rotate and how light bends around massive objects, a phenomenon called gravitational lensing. But dark matter doesn't emit, absorb, or reflect light. We can't see it directly, but we feel its gravity. Dark energy, on the other hand, does the opposite. It doesn't pull, it pushes. And it doesn't clump around galaxies. It's evenly spread throughout space. Even in the deepest voids, where there's almost nothing, dark energy is still there. It's not attracted to mass. In fact, it seems to grow stronger as space expands. So while dark matter helps structure the universe, building galaxies and clusters, dark energy is slowly tearing that structure apart. Now, what could dark energy actually be? Scientists have a few ideas. The leading one goes back to Albert Einstein. In 1917, when he was developing his theory of general relativity, he realized his equations predicted that the universe should either expand or contract. But at the time, everyone thought the universe was static, unchanging. So Einstein introduced a cosmological constant, a kind of anti-gravity force that could balance gravity and keep the universe stable. Later, when Hubble discovered the universe was expanding, Einstein called this his greatest blunder. But here's the twist. The cosmological constant might have been his greatest insight. Today, many physicists believe that dark energy ices the cosmological constant, a constant energy density built into the vacuum of space. According to quantum physics, even empty space isn't truly empty. It's filled with tiny fluctuations, virtual particles popping in and out of existence. This gives empty space a kind of energy, called vacuum energy. And if that energy is real, it could be what we're calling dark energy. The problem? When physicists try to calculate how strong this vacuum energy should be, the number they get is trillions of times Clay's larger than what we observe. That's one of the biggest unsolved problems in physics. Another idea is that dark energy isn't constant at all. Maybe it's a field, something that changes over time. Scientists have given it a name, quintessence. Like the Higgs field or the electromagnetic field, quintessence would be a new kind of energy field that fills the universe. But unlike the cosmological constant, it could weaken, strengthen, or even reverse over time. If that's true, then the acceleration of the universe might not go on forever. Maybe one day, dark energy will fade, and gravity could take over again. Or maybe it will grow stronger, leading to a big rip. A scenario where dark energy becomes so powerful that it tears apart galaxies, stars, planets, and eventually even atoms. We don't know. There's no evidence yet for quintessence, but it's a possibility. And then there's a third, more radical idea. Maybe dark energy isn't real at all. Maybe our theory of gravity is incomplete. Einstein's general relativity has passed every test we've thrown at it, from black holes to gravitational waves. But maybe, on the largest scales, gravity behaves differently. Some physicists have proposed modified theories of gravity that could explain the acceleration without needing dark energy. But so far, none of these theories match the data as well as the standard model does. So what's the evidence for dark energy beyond those supernovae? There's a lot. One of the strongest comes from the cosmic microwave background, the afterglow of the Big Bang. Satellites like Planck have mapped this faint radiation in incredible detail. It shows us what the universe looked like just 380,000 years after the Big Bang. From these patterns, we can calculate the total amount of matter, energy, and curvature in the universe. And the numbers only add up if dark energy is real, about 68% of the total. Another piece of evidence comes from baryon acoustic oscillations, a kind of cosmic ruler based on sound waves from the early universe. By measuring how galaxies are clustered across space, we can see this ruler in action. And again, the data confirms that the universe is expanding faster over time. More recently, a puzzling conflict has emerged, the Hubble Tension. Different methods of measuring the current expansion rate give slightly different answers. One comes from the early universe, based on the CMB. The other comes from nearby supernovae and stars. They don't quite match. Some scientists wonder, could this mean dark energy is changing? Or is there something else we're missing? It's an open question, and one that could lead to a major breakthrough. Now, let's bring this closer to home. Does dark energy affect us? On Earth? In our solar system? The answer is, not really. Dark energy is incredibly weak on small scales. It only becomes noticeable when you look at the vast emptiness between galaxies. Here, gravity dominates. The Earth is held to the Sun by gravity. The Sun is held in the Milky Way by gravity. Even the Milky Way and Andromeda galaxies are pulling toward each other. They'll collide in about 4 billion years. Dark energy isn't strong enough to stop that. But on the largest scales, between galaxy clusters, dark energy wins. Right now, galaxies beyond our local group are already moving away from us faster and faster. One day, if you could look up at the sky, you might see only the Milky Way. All other galaxies vanished beyond the horizon of visibility. The universe would appear empty, and in the far, far future, trillions of years from now, even the stars will burn out, black holes will evaporate, and space will keep expanding, colder and darker, until there's nothing left but silence. This is called the Big Freeze, or the heat death of the universe. And dark energy is the reason. But here's something beautiful to consider. We live in a rare moment in cosmic history, a time when we can still see the past. We can observe the cosmic microwave background. We can see distant galaxies. We can trace the story of the universe back to its beginning. In the far future, that evidence will be gone. Any civilizations that arise then may never know the universe had a Big Bang. They'll see only darkness. So, in a way, we're privileged. We're here at a time when the hum of dark energy is just beginning to dominate, but not so much that it's erased the story of where we came from. And that gives us a responsibility to understand, to explore, to ask questions while we still can. So what is dark energy? We don't know, not yet. But we know it's there. We see its effects. We measure its influence. It's the most dominant form of energy in the universe, and it's shaping the destiny of everything. The cosmic hum isn't a sound we can hear, but it's a metaphor for something real. It's the quiet push of space itself, stretching the cosmos into the unknown. And while we may never fully understand it, the search for answers is one of the most profound journeys in science. Because every time we look up, we're not just observing the universe, we're listening to its deepest secrets. If this idea moves you, if you feel that quiet hum in the silence of space, then share this video, talk about it, ask questions. Because science isn't just about facts, it's about wonder. It's about standing under the night sky and realizing how much we don't know and how beautiful that mystery can be. And if you want to keep exploring the universe with us, the hidden forces, the unanswered questions, the stories written in light and time, then subscribe. Turn on the bell. Because there's so much more to discover. The cosmos is humming. Are you listening?